Hello everyone, welcome back to LeetCode Daily Live, where I do the daily question, raw and uncut. So we have a medium today called Lexicographically smallest equivalent string. So you're given two strings of the same length, S1 and S2, and a string base string. So you have three strings. How long are they? So all of them are only 1,000 characters long at most, and they're all lowercase English characters. Okay, so we say S1I and S2I are equivalent characters. So if you have A, B, C, and C, yeah. So S1 is if S1 is A, B, C, and S2 is C, D, E. We have A is equal to C, and B is equal to D, and C is equal to E. Okay. Equivalent characters follow the usual rules of any equivalence relation. So the same word is equal, the converse is equal, and you have transitivity, which basically means like if A is equal to B, B is equal to C, then A is equal to C. Okay, that's quite mathematical, but sure. So for example, given the equivalency information from here, we can deduce that the base string EED and AAB is the lexicographically smallest equivalent string of base string. So we want to return the lexicographically smallest equivalent string of base string by using the equivalency information from S1 and S2. Right, so let's look at an example. I think I understand what's going on. So we have Parker, Morris, and Parser. So I think like for the character P, well, because P is equal to M and M can't get any smaller, that's why like we have M here. So basically, you want to find the string that's equivalent, like using S1 and S2. So the string that's the smallest, that is equivalent to base string, with S1 and S2's rules. So basically, yeah. So I understand the question now, and I think what we just have to do is we have to find out for each character what is the smallest what is the smallest character it can get to. So if we look at like A, B, C, and C, D, E up here, so you can imagine like C connects to A, and then D connects to B, and then E connects to C. So what does that mean? Well, if I make this into a graph, we can actually draw something like this, right? So that means for the character E, we can get all the way to A. And for the character D, we can get all the way to B, and C we can get all the way to A. So if we have a string like on the example, which is something like EED, right? Well, because E can turn into A, and E can turn into A, D can turn into B. This would be our lexicographically smaller string that's equivalent, right? So yeah, so basically there are tons of ways to do this, but I think what we can do is we can just form a graph, like for these relations. So we will have 26 nodes, and we will have 26 nodes and 1,000 edges at most. Yes, and then I think for each character we just have to BFS out to so you can also have something like E goes to Z, and then like Z goes to A, right? Like you can have something like this as well. So it doesn't only just go downwards, meaning that we really should BFS out for each character, and we want to get the smallest character. Yeah, but yeah, simple BFS would work here. And then the rest should be very simple. Like once you know for each character what's the smallest it can get to. So yeah, let's just code this out. So we have I think what we want is we want a char to int function, just to make things a bit easier. So let's call it like c to I, just like in C or C++, I think. So we have a character, which really is a string, but like, but it should return an int, right? So we just want to return the ordinal of the character minus the ordinal of A, and that should give us the integer we want for that number, for that character. And so we have an adjacent list. So we have 26 nodes. So the reason we only have 26 nodes is because we only have the characters A to C, right? So and then we have to form edges between them using this here. Yeah, actually my drawing is like a tiny bit wrong here because it's bidirectional. So technically, like, you can go back up as well. So like, for example, if D connects to E, well, actually then in that case B can reach A, like using this path, right? So you actually have to be mindful of that as well. And like, we have to make bidirectional edges basically. So now for I in range length S1, so we can get the character of so yeah, we can get S1I, and then we can get S2 S2I. So that will be the two characters, and then we turn it into the corresponding number. So it would be like, so A corresponds to 0, B corresponds to 1, and so on. So now that we have this, we want to connect adjacent list, append this character, and we'll do the same for this here. So now we have connected the bidirectional relation, and we can find min char for the min char for each of the character. So I think, yeah, we'll just do I for I in range 26. Well, because every character is equivalent to itself at least, right? So like, for the character A, well, like A corresponds to 0 here, right? So 0 can connect to 0, 1 can connect to 1, and so on. And now we just have to loop through each of the characters. So I want to do a BFS. Yeah, current min would just be I. Maybe we don't need this at all. Like, we can just append, but whatever, it should be the same. So current min, and then we should have a queue that only has I in it so far, and a scene set. Well, technically using an array could be better because set has a bigger overhead, but whatever, it's fine. So while queue, so for node in queue, yeah, we need a new queue, of course. If node in queue, for node in queue, well, first of all, if we have seen the node already, so we want to continue. Otherwise, we have reached a new node, and we want to add that into our new queue. So new queue dot append node, and we also want to mark it we want to mark the node to be seen. Yes. And then like we can just do q is equal to new q at the end here after we have gotten all the new nodes. Yeah, but then we also want to compare like with the current mean, right? So what we can do is we can just do current mean is equal to the minimum of I on node. So at the end, after we broke out of this loop, I think we should put that in there. Yeah. So after we like looked at all the possible nodes, we just want like we will have the minimum that we have seen, and we can put it into like min char. So we have min char I think is equal to current mean. And now at the end, we have a result string. So we want to do it as a list first, because adding characters in the string is on in Python. So that's why we want to use a list. So now for character in base string, res.append. So we want the minimum for the character C. So how do we get that? So it will be min char C to I. So we map the character into the number first, and min char should get the minimum it can get. And we want to turn it back into the character. So how do we do that? Well, we can just have another function. So I to C. So I would be int, and then it should like return a string. I think this is like a possible type annotation to mark that it is a string. Maybe char works as well. Let's see. I'm not sure if char works. Yeah, I think maybe string one. Whatever. So we want to return so I plus ordinal of A, and then we turn it back into a character. So yeah, so we can just do I to C here for that character, and at the end we can just return we can just join the characters together. So let's see if this string one thing works. Yeah, okay, it doesn't work. So we'll just leave it as a string. Yeah, I think there's a way to annotate a string, like a character or something. Okay, I'll put it parser. That's not good. What did I do wrong? I'm range 26. Result. So for C in base string, let's print out minimum character. Print min char. Okay, so I didn't actually change anything. Is it because, okay, let's make sure adjacent list at least works. So print adjacent list. Okay, adjacent list seems to work, I think. Yeah, it does seem like it works. But so something is up here. So new queue. So while queue. So we do have an item in queue for node in queue. If node in scene, so it should add that in. Okay, what's wrong with my BFS? New queue. Might just print out queue every time. Okay, we just got 0011 and so on, which is quite strange. Append node. So actually, what nodes are we getting? We should also print out I here. So scene.add node, current min. But why is it not adding to our new queue? Maybe I can print out the new queue. I'm sure some of you guys are like screaming at me, cause like you see the error. Yeah, okay, so it doesn't add anything, but A does have a yeah, it does seem like A has it has one thing in there, right? So why does A only connect to itself with like the parser thing? So yeah, Parker. So A connects to O, and we saw that it works. That's very strange. Am I using the... Oh. I did an extremely dumb thing. I'm not using the adjacent list at all. So actually here, what I should do is instead of doing for node in queue, well actually yes, I have to do for node in queue, but I also should do for next in adjacent list node. So that's actually the thing that gets us the it is neighbors, right? So next, and then next. What about now? No, it still doesn't work. Okay, what's... Now I'm kind of confused. So adjacent list node. I guess we can print out adjacent list node up here. And if we have seen that already, we will not look at it. Okay, so we do have 14 this time. Okay, let's just find a character that we know works like straight away. So R goes to R. It might be like some... Yeah, I'm not sure, cause like my logic is definitely correct, but yeah, something is up. So like when we look at A, we'll get O, but O doesn't connect to anything else. So that makes a lot of sense, like for A to be the same. But what about for P? P should connect to M, right? Oh, is it because we need to get the current minimum instead? Is that why? Yeah, okay. Just so many bugs that I'm just running into. That could be avoidable if I paid a bit more attention. So it should work now, unless we run into some loops. Okay, yep, it works now. So yeah, I wasn't my best, like running into lots of bugs doing BFS, but yeah. Nevertheless, I'll talk about how I thought about this solution. Like on hindsight, if you just look at the two strings, like it doesn't tell you anything about graphs, right? But I think like graphs are actually very powerful, and like you can apply them in like lots of other ways as well. Like I'm sure there are ways where like you can keep updating each of the character, and like to keep getting the minimum or something. But like you could run into issues there, right? But what if I just but yeah, what if I guess like the way I thought about using a graph is visualizing what's actually happening. So like because if like remember transitivity, if A is equal to C and if A is equal to B and B is equal to C, then A is equal to C, right? Um so if we use this, well, what do we know? We know that when something is equal to something, they're in the same group, right? And so therefore B is also equal to C. So that means A, B, C are all in the same group. So uh the word same group should kind of like make you think about connected components. And well, how do we find connected components? We can use a graph, right? That's like one of the most like basic graph algorithm. Like just do a BFS or DFS out to like get all the connected components. And we just want the minimum. We just want the smallest character in that component, right? So that's how I thought about graph. And like for the other stuff is mostly just implementation, and it's quite simple. So yeah, I think other than me missing like $100 in my BFS, it's a pretty straightforward question. So yeah, thanks for watching, and I'll see you tomorrow.